Good morning. I'm Claudia Di Vizia, and I will present the paper entitled A Hierarchical and Modular Agent-Oriented Framework for Power System Co-Simulation. The smart grid is a complex system that encompasses many fields of expertise. Indeed, co-simulation platforms are emerging as a tool for testing future scenarios, thanks to the ability to couple domain-specific simulator in a broader context. However, while most simulators focus on technical knowledge, we have to remind that the energy transition involves complex dynamics that require also a social scientific perspective. Indeed, the Bridge, a European Commission initiative which gathered the issues encountered in pilot project, underlined also the need for understanding and strategizing collective action of citizens. Therefore, it involved experts with different backgrounds. In simulation, the residential user become a core element. Indeed, simple residential user might adopt photovoltaic panels, becoming prosumer, or might join and create an energy community participating in a peer-to-peer market. Even as a simple customer, they might be part of demand-side management programs. A proper methodology to model a user and its behavior is agent-based modeling. ABM can be described in brief as a tool for simulating real-world phenomena, or as a method which examines the interaction of entities and which falls on a spectrum with fuzzy boundaries. As an example of this fuzziness in the literature, we found an ABM for the shift of appliance during off-peak hours according to a probability under a time-of-use tariff system. Here, interaction between agents are not considered. As a first step, we want to propose a neutral agent-oriented framework that, based on the additional model, can be considered an ABM or a tool for testing other strategies. From other work, we determined some key requirements for the framework. Waldsberg et al. Present an ABM to simulate human behaviors and the changes implemented in NetLogo, suitable for non-programmers. However, the simplicity of the programming language could limit the complexity of the model. Therefore, we wanted to have a good alternative. We noticed that others found out that, for example, ABM for residential buildings has been designed for a specific use. Thus, we want our model to be reusable. Others propose a multi-resolution ABM with 3 hierarchical levels. They plan to utilize the model for demand response strategies and did not claim that the framework can be used in co-simulation. So we want to be able to select the level of detail and work in co-simulation. To sum up, there was a need for a framework that eases the test of new residential strategies and foster the comparison among these latter by incrementally adding new models that tackle different aspects of the agent or easily changing simulators and strategies in a plug-and-play fashion. We can now zoom in on our agent. The agents are created into IOMAS, a Python library where the logic of the agent needs to be implemented. Thus, we standardize this agent with some basic characteristics, such as the agent ID and the registration process. Thus, at the beginning of the simulation, the uppermost level of interest is created. Then, the level below is built, receiving as input the desired upper agent address. Thus, the lower level agent registers to the upper ones, and so on. Depending on the type of agent, it will have different attributes and methods. Thus, using the principle of inheritance, each agent will be characterized by the proper behavior. We will focus on the energy provider, the household, and the user agent for the proposed examples. The core mechanism revolves around 3 blocks, namely the real-time, the initial intention, and the change blocks. The real-time produces data for that time step, while the initial intention produces data for the next end step and defined by the user. So, in this way, we will create the expected baseline, and we will keep this in memory. Then, if we want to observe a change against the baseline, we will use the change block. The change relies on the rule models, separate models to model a particular change, and that we will analyze later on. The household and user agent are an agent-oriented and step-based implementation of the work proposed by Bottaccioli et al. Thus, the user agent has to faithfully reproduce the behavior of a single person. To this end, a sequence of action generated using a semi-Markov model where the states are the daily activities retrieved from large sample surveys are used. If the scenario includes household agents, the agents belonging to the same family are associated with the corresponding household agent through the initial registration process. The resulting behavior of the whole family can be translated into energy consumption through a separate model that simulates the usage of own appliance. The energy provider agent aggregates the consumption of its customer to study macroscopic effects and can inform or request other information. Thus, the electricity consumption can be generated and retrieved at each time step, or we can use the initial intention mode. In the initial intention mode, first n time steps are simulated. Then, the corresponding electricity pattern is saved in memory, acting as a baseline. Starting from the baseline, the strategy or the new behavior can be simulated, obtaining a new electricity consumption pattern. Using the state consumption vector, the simulation proceeds in time, returning at each time step the corresponding consumption value. The rule models available are the behavioral model, which aims at simulating in a simple manner the behavioral change of an house, which is exposed to dynamic tariff. So similar to Valet et al., this model anticipates or postpones the usage of appliance during the lowest tariff according to a probability P. The optimization model, which can be considered in this case study as an optimal schedule of the appliances that can be shifted in time, minimizing cost, consider balancing constraints and the time allowed for the shift. The formulation is dynamically configured based on the resource considered. Being a separate model, this strategy can be easily changed with more complex ones. If we consider the baseline as a forecast, another model could be, for example, the add random noise model to add an error to the provision. We are now ready to look at some examples. We start focusing on a single house that owns a home energy management system which optimally schedules the turning on of the appliance during the day. Thus we need one household agent and 3 user agents, for example, the initial intention change blocks, and the optimization rule model. We suppose that the household is not under a flat tariff. Therefore, the appliance is optimally scheduled in the cheapest time slot, resulting in a benefit for the household. However, we might wonder what are the consequences of many households owning a home energy management system. Therefore, we will focus on the energy provider agent, which aggregates the consumption of 2,000 households. We can observe the effect of a home energy management system when allowing 3 and 5 hours of shift. As the time allows increased, more appliances are scheduled in the best time slot, potentially creating an issue for the energy provider. To provide the capability of our solution in working in a co-simulation environment with an external simulator, we consider a home energy management system of an household with a PV generation. Thus, we exploited an external PV panel simulator, the Mosaico simulation framework, and its APIs to couple this PV panel simulator with our agents. The washing machine was initially scheduled during the evening. Thanks to the AMS, it is anticipated in the morning during IPV production. We also check the power balance. In yellow, it is possible to observe the PV production. A good amount of it, the portion in green, is sold to the main grid, while the rest is used for self-consumption by the prosumer. During dark hours, instead, the electricity demand is satisfied by the main grid, the area in orange. Moreover, we perform a second simulation for an entire week, which highlights the tendency to anticipate the use of the appliance during daylight hours to save up. The change model can be implemented also into an upper layer, which might, for example, implement a centralized strategy. Therefore, for example, we could reuse the centralized optimization proposed in our previous work, while we try to learn preference by asking for a confirmation for shifting an appliance. Thus, after the step, we can use a simple get-set methods to pass other information. Here we have another example of our recent work on energy communities. In this case, the shift of appliance was not considered. Indeed, the purpose of this work was to propose an optimization flexible enough to tackle both energy community with shared resources and peer-to-peer market in a non-shared resources community. We had the input data read from a file, the flexible optimization, and the evaluation of KPIs. In this case, the flexible optimization could be used by the change block. Total savings and another community KPI could be evaluated by a community manager agent, while the input data could be generated with the household and the user agent, similar to the previous scenarios. Thus, we could easily expand the scenario by including the shift of appliances and more interaction among agents, which affects the input parameters, as for example the reservation prices of each single user in the peer-to-peer market. We change again the scenario. In this case study, the energy provider agent exposes customer to time use tariff. Thus, we need the behavioral rule model and all the three levels. On the left, we have an example of a shift during the low tariff. On the right, we have 150 household agents and 334 user agents. And the probability of changing the energy consumption equal to 0.5. We simulate consumption for 1 week and we plot the average electricity consumption over the 24 hours, comparing the initial consumption of the households and the one with two extreme behavior. Appliances randomly turned on inside the low tariff period, and appliances turned on immediately before the beginning of the highest tariff. The real behavior would stand somewhere in between these two curves. Thus, the framework allows us to make consideration of different scenarios. To sum up, we presented a hierarchical agent-oriented framework to ease the reusability of previous developed models, to test new strategies, and allow the comparison of different optimization and behaviors. We consider the example provided as a prerequisite and as a starting point with respect to the more complete definition of ABM. The framework is in the early stages of its development. Existing agents need to be improved with more complex behavioral aspects and interaction. A new actor should be introduced, such as the industries. In view of cooperation with researchers with different backgrounds or companies with more data, the framework can be used to understand the consequence of what-if scenario based on the technological adoption of the behavioral changes observed or predict. Thank you.